Dr. Aritra Roy has completed his doctoral research in the Department of Electrical Communication Engineering at the Indian Institute of Science, Bangalore. He was a postdoctoral researcher at the Université de Bretagne Occidentale, UBO, Brest, and is currently at Sorbonne University in Paris. His research interests focus on microwave engineering, wideband and multi-band antenna systems, beam scanning antennas, and metasurface assisted wireless links. Besides publishing his works in national and international conferences and journals, he has been granted several patents in collaboration with industry partners such as Thales EMS, Thales LAS, and Thales Alenia Space.
Thank you for this warm introduction. So, good morning everyone. The title is a study on efficiency and frequency scanning in corrugated leaky wave based leaky wave antennas. Here I shall be discussing about the developments on fast scanning leaky wave antennas in our laboratory. So in typical millimeter wave based array systems, where we scan, where we have to cater different users sitting at different locations by moving the beam across. But before the communication is established, we have to sense the user location. Now, if we use the same phase array to sense the user location, that means the entire frequency spectrum will be guided at different angles. In this way, the issue is, since we are guiding the entire spectrum at different angles, so overall scanning time may be high. Also, maybe the background computation for the direction finding may be more. So in this way, we have more latency, we may introduce more latency into the system. So to cope up with this issue, another layer of scanning can be appended, in which instead of guiding the entire spectrum towards each user, a single frequency is guided at each user. As you can see, F1 till Fn is guided from user from theta 1 to theta n. So this is nothing but a leaky wave antenna system which actually propagates the fast waves through the antenna and generate radiated beams, directional beams. And the beauty is it can divert different frequency beams at different angles. So we actually focus our investigation on fast scanning capability of this kind of antenna. That means we want to see that, actually we want to scan the entire space over a narrow frequency band. That means we want to maximize the factor delta theta with respect to the frequency. And as the theory suggests, if we want to maximize the delta theta, we have to maximize the delta beta. So that's why I shall be discussing about a special type of structure, which is a corrugated waveguide loaded structure, which has a high delta beta with respect to the frequency. Accordingly, here is the top outline. First, I will briefly demonstrate the structure of the antenna. Then I will discuss about the unit cell analysis of the antenna in presence of the radiating slot and without the radiating slots. Then I will briefly show the antenna performances before the conclusions. So this is the typical antenna that we are using. As you can see, it is nothing but a square waveguide structure of dimension A by B. The corrugated section is placed in the bottom wall of the antenna, whereas in the top wall of the antenna we have the radiating slots. Now, the propagation constant is obviously complex. It has both alpha and beta values. The alpha is accounting for the total losses. Now, in this structure, the total loss is dominantly due to two features. One is due to the loss through the radiating slots. Another one is the losses inside the material. The beta is a wave number which dominantly defines the scanning velocity of the antenna. So here is the schematic of one unit cell. So obviously one unit cell consists of a rectangular waveguide section as well as one corrugated section. Now I will move to the unit cell analysis of this unit cell without the radiating slots. Analyzing the unit cells means just studying its dispersion behavior. So we have a lot of different eigenmode solvers available in CST or HFSS. We use something similar, and as you can see here, the dispersion response. The dispersion response falls into the fast wave between 25 to 29 gigahertz. That means we have 4 gigahertz of bandwidth associated with this unit cell. But the beauty of this unit cell is we can get two different beta values for which we can scan from both sides till the end file. That means we can scan from plus minus in between plus minus 90 degrees. Now there is a drawback using these commercially available eigenmode solvers. And the drawback is we cannot compute the alpha values. Now alpha values means alpha from the material we cannot introduce or cannot compute. Also, if we place a radiating slot, the effect of the slot is not captured. Ultimately, the loss is not captured. Now, to cope up with that problem, what we do? We simply take an S parameter approach where we calculate the S parameter, then calculate the ABCD parameter, and then the alpha beta values. And that is how we can calculate both the alpha and the beta of the unit cell. But again, there is a problem. As you can see, the S parameter results doesn't match well with the eigenmode results. Now the question is why? Because in S parameter results, we just simulate a single unit cell. That means we do not consider the mutual coupling inside an array. So how to incorporate this mutual coupling into this dispersion analysis of a unit cell? For that, we have proposed this very simple technique in which we take n and n plus 1 number of unit cells, calculate their ABCD matrices, and from that we actually calculate back the ABCD matrix of a single unit cell. By doing so, we have achieved a dispersion response which actually matches with that of the eigenmode solver. So the bottom is, the summary is, we can say in this process we actually get a very accurate calculation of beta, as well as we can also calculate the alpha of this unit cell, which cannot be done using commercially available eigenmode solvers. Then we have investigated the fast scanning capability of this unit cell. As you can see, the height of the corrugation is varied. And if you see, if we increase the height of the corrugation to 9 mm, typically the fast wave band can be restricted between If we increase the height of the corrugation to 9 mm, you can see the fast wave bandwidth can be restricted between 25 to 26 gigahertz. That means simply by increasing the height of the corrugation, we can reduce the antenna bandwidth from 4 gigahertz to 1 gigahertz. But the problem is, if you look into the alpha behavior, the alpha behavior becomes extremely frequency sensitive. That means the alpha value changes very fast with frequency. So if we implement an antenna using this unit cell, there is a probability the antenna will not have a flat gain, instead it will have a varying gain. We also looked into the same unit cell in a slightly different way. We have find out different combination of P and H. P means the periodicity of the unit cell, and H is the height of the corrugated section. And what we saw, if we want to maintain the same beta response, and if we increase the value of P, the value of H reduces. That means for the same dispersion response, if we use a longer period, we can have a shorter, geometrically shorter corrugation. At the same time, since the corrugation size is shorter, the overall metallic area inside the waveguide is less. And since the overall metallic area inside the waveguide is less, the loss is less. The alpha value is less. And as you can see, with the increase in the value of P, the alpha value slowly reduces. Although the overall value of the alpha is significantly small, and we shall see its effect in the following slides. Here is the unit cell analysis using a radiating slot. Here, the section we simulate actually consists of a single radiating slot and multiple corrugations. Here, the slot periodicity is set in a way so that we have only a single beam. That means we have only a single harmonic throughout the operating band. Here also we have changed the value of H and consider two different cases. One is lossy, one is lossless. Obviously, in the lossy case, we consider the material loss, and in the lossless case, we don't consider the material loss. And we have some typical observations. First observation is, if we increase the value of H, the fast scanning bandwidth can be reduced. This observation is same to what we got in the last slide. Another one, if we introduce loss into the structure, the beta response does not change, although the loss is captured into the alpha response of the unit cell. As you can see here, obviously alpha for the lossy case will be more than alpha for the lossless case. This is straightforward and intuitive. And also we saw that when the value of H is small, when the corrugation height is small, in that case, the overall loss is dominated by the leakage. Whereas when we try to implement a fast scanning antenna, we have leakage as well as the material loss. So there may be a trade-off between the loss and the scanning rate. That I shall be showing next. So to get some idea about the probable radiation efficiency, we have calculated the theoretical radiation efficiency, which is nothing but the ratio of these alphas for lossy and lossless cases. Here we have observed that if we increase the value of P, at the same time if radiation efficiency is increased. That means if we have a smaller corrugation periodicity, the efficiency is less. But why so? So to know that, we have proposed a sort of a qualitative understanding is that when the corrugation are close to each other, that means the metallic walls are close to each other, it confines more electric field. So most of the electric field are confined near the corrugation, less electric field on top wall of the waveguide. That means if we make the P small, we have a less radiation and hence a less radiation efficiency. So this may be one of the qualitative explanation why we lose the efficiency when we have small P. Now let's look into the antenna overall performance. The antenna we have simulated for 2 GHz band. Throughout the band we have an S11 which is less than 10 minus 10 dB, so the antenna has good impedance matching. When we look into the S21 value, actually the S21 curves follows the trend of the alpha curve. Okay, and since our alpha was not flat, S21 was also not flat. Now if we look into the radiation efficiency, here also we have a similar observation. The radiation efficiency also follows the alpha. So alpha is not flat, radiation efficiency is also not flat. Now when we look into the overall realized gain, this is a function of the efficiency and the impedance matching. So the overall pattern is slightly modified. Although for all of these cases we can see that if we increase the value of P, we marginally modify the radiation efficiency and the antenna gain. That is, we increase the radiation efficiency and the antenna gain. If we look into the radiation pattern, I started with 0 to 90 degree with the hope of 0 to 90 degree scan, but we ended up between 4 degree to 58 degree. That means right now we can scan approximately 54 degree of angle over a band of 2 GHz. So we have approximately 7 degree of scanning per fractional bandwidth. When you look at the envelope of this radiation pattern, which is nothing but the antenna gain, and we can see the antenna gain is not constant. It varies between 8 dB to the peak of the gain. So this is an issue obviously. Now if we look into the scanning rate, what we see is at low frequency, the scanning rate is low. That is, at low frequency for a 200 MHz band, we have 4 dB of scanning rate, but for the same band at high frequency, we have a higher scanning rate. Why? The result lies into the dispersion diagram. If we look into the dispersion diagram and take two different sections, at low frequency you see the change of beta is slow. Change of beta with respect to frequency is quite slow. Whereas at the higher end of this band, the change of beta with respect to the frequency is quite fast. So we can get a higher scanning angle if we utilize this part, but unfortunately, it falls into the small wave region. So this part does not radiate. So how to make a radiation out of this region? For that, we have actually generated a beta minus 1 harmonic. And we have said we have generated the beta minus 1, beta minus 1 harmonic was there, but we just controlled its position by controlling the periodicity of the slots. And in that way, you can see after 27 gigahertz, we are able to place the beta minus 1 harmonic inside the fast wave mode. Now, when we simulated an antenna with this mode, what we saw is quite interesting. This time, we have approximately 44 degree of scanning range over only 200 megahertz. That means this time the scanning rate is significantly high. With beta minus 1 harmonic, we have approximately 63 degree per fractional bandwidth, which is approximately 9 times of what I showed in the last slide. Now, obviously, if this is so beautiful, there must be something extremely bad, and the bad thing is the gain. When we have a high scanning rate, we sacrifice the antenna gain. Now, why? So, to search for why, we just looked into the different parameters, such as this parameter and the radiation efficiency. We saw that the overall radiation efficiency is low. Why? Is because the operating band we have selected is extremely close to the band gap. And as we are approaching the band gap, the overall propagation through the waveguide is seen. So that is one of the reasons why the S11 is degraded at high frequency. Also, there are associated losses inside the waveguide, which increases by increasing the wave number, because the wave inside the guide reflects a lot of time since the beta is very fast. So that is one of the reasons why we have high losses. So these are some of these qualitative idea what we have, but we want to see into this structure in a more quantitative way. That means we want to quantify these phenomena using numbers. So that was all from my side. In conclusion, for the first part, I have shown a unit cell analysis where we introduce the mutual coupling effect into the dispersion characterization of the unit cell. Second, I have shown an antenna that radiates a beta naught harmonic. The structure is compact, it has good radiation efficiency, but it has a low scanning rate. We can significantly increase the scanning rate by using the beta minus 1 harmonic, but at that time we lose the radiation efficiency and the compactness of the tube. So there is always a trade-off till now between this scanning rate and the radiation efficiency. So next we want to look into this factor in a more quantitative way. That how can we overcome this reduction in gain close to the open stop band? And after that, we want to adopt this antenna for real-time applications. We are looking for an application for angle of arrival estimation. And here is the fabricated prototype you can see, which is made using DNMS technique. So here is the team. Kindly revert back to us or write back to us if you are interested in our work or if you want to know something more about this. Thank you for your kind attention, and thank you IEEE and EuMW for organizing the meeting. Thank you.
Thank you, Dr. Aritra Roy. So the talk is now open for questions, and I think we have time for one maximum. Thank you.
Hello, that was a really nice talk actually. I have one question. You talked about the difference between these p-values or the difference between slots. Have you tried not doing it evenly, but like uneven slots, where you have like a few slots that are further apart and some others that are like closer spaced to each other?
See, the slot periodicity actually determines where you will place the harmonics. So till now we are just restricted with minus 1 harmonic, so we have only tried evenly spaced slots. But this may be something of extreme interest activities. And obviously, I shall be responsible my Thank you.
Yes, thank you.
Okay, thank you. Yeah, it's 11:20, so we have to move on with the next talk. Thank you again.